that, for instance, in response to more demand for goods and services, you're going to have, that demand is going to be satisfied in the sense that consumption as a fraction of GDP goes up. Output goes up. Now that output has to be produced, so wages are going to go up, and so that means marginal costs are going to go up. As an effect or as a consequence of higher marginal costs, you all now, the experts, are understanding when in a New Keynesian model marginal cost goes up, what happens to the inflation rate? Inflation rate is going to go up, exactly, right? So inflation is going to pick up as a consequence. And then the central bank responds to that by raising the nominal interest rate and trying to stabilize the economy. Now, interestingly, this is a boom. Now, but we know in this model, when you have a boom, that produces more emissions. And that's what you see here. Right? The stock of carbon in the atmosphere goes up. So the derivative of that is the emissions. Right? This is the stock, and then the derivative of that is the emissions. Okay? So new emissions go up, but because the stock is very high, the additional emissions have quantitatively a relatively small effect because the stock is so high, you're going to have a couple of new emissions, but you're going to increase the amount of emissions in this economy, and thereby the stock of M is going to go up. So that's basically how you can think about how this shock affects the economy. In general, what you want is, so you have to interpret all these numbers in levels. Okay? There's no percent deviation. So you can, of course, now compute what is the percent change, right? You can compute what is the percent change in output, right? By computing the log differences or the percent changes of this blue line, right? You take all these numbers and compute the percent deviation changes, and then you get the growth rate, for instance. Right, so this is the demand shock. Now I want to show you how you could, for instance, also look into other shocks. Right, the model has different shocks. So let's take a look at it. How do you do this? The way to do this is the following: you have to locate what shock you want to study. And we have studied this one now, the preference shock. We did the inflation shock or the cost push shock and the monetary policy shock in the other classes. You could do this yourself maybe this afternoon. Maybe let's look at this emissions shock because we haven't actually studied that. So where does this emissions shock show up? Well, it's in the law of motion for the carbon, stock. It's this like there's a volcano erupting or there's some exogenous increase in emissions that is not production related. That's what this emission shock is. So let's see how that looks like, what happens in this economy. So the way to do this is that you have to think about this as Epps tau is the no, I think that no, what am I doing? Okay? So we could look at that emission shock, right? And okay, let's do that. Let's do that. And the way to do this is, we want to do the following. You want to go to the place where the shocks are, and my advice is, let's copy this. Just copy this. And then paste it underneath, and do 2 forward slashes here. So we preserve our original line. And then we want to do EE. This is the shock to the emissions. And then we run the code. That's it. So copy this line, change the shock name, and then run it. And then this is going to give you how does this economy adjust if you have an emissions shock. So there is a volcano hitting or whatever that increases the emissions, and you see this is quite persistent. So this is more persistent, that shock, than the other shocks. And then what you see as a consequence now is because of that emissions shock hitting, right, there's going to be more emissions, and those emissions are going to be detrimental to productivity. Remember, right? Output is a function of emissions in a negative way. It's the externality. If emissions go up, the economy is heating up, the planet is heating up, and that's going to affect productivity in a negative way. Then you see output is going to go down. And that means that inflation is going to go down on impact, the interest rate is going to go down, consumption is going to go down. So you can get this, so to say, understand each shock separately, one by one. There is a, you can of course have also a combination of shocks. You don't need to go ahead.
Sorry, in here inflation goes down initially on impact because output go down, right?
That's right.
But
That's the demand.
As you have higher M, right, you have
Yeah.
the process of inflation.
Exactly.
But can we look at the decomposition through the
You can, and we're going to learn that later today. That's exactly the plan. You can always decompose what force, where do you see greenflation, where do you see climateflation coming in? Absolutely. And this is more the climateflation, in the medium run there, when inflation basically goes up, right? In the short run, there's this bad demand effect. Because of lower demand, inflation is popping down. But then going forward, it's going to rise. Precisely what you have in mind. You can decompose that, and we're going to learn how to do that in the slide that we're going to discuss later today. Now then what you can also do is you can do different combination of shocks. You can say like, let's have two shocks at the same time hitting. Okay? So you can have a demand shock hitting at the same time when you have an emissions shock hitting. You can have that as well. Okay? So you just activate both shocks and then you run the code. And then you see you get, so to say, an impulse response where you see when two shocks are moving, like this B shock and the E shock, they move together at the same time, how the economy is affected by the combination of the two shocks. So you can have simulations with different shocks at the same time. Last but not least, and I think that's the last little exercise I want to do with you, let's copy one line again. Okay, let's just copy one line and do 2 forward slashes here again. And let's put in that. Okay. And then now I want to do the tau, the tax. So E tau is the tax. This is the carbon tax. And let's examine what happens in this economy if you raise carbon taxes. Carbon taxes go up. And they go up one time. So let's study that. And so we're going to run this code. And then what you're going to see as a result, you're going to see that it's not even plotted because there is no tau process plotted. So this only plots the endogenous variables, and the tau would be in here, but tau is just a shock. It's like this one-time shock. So that's why you don't see the path for tau here, right? So what we're doing is that there is no like S tau or something like here, right? That's right, exactly. But there is no E tau that we can plot here, yet in other words, it's just the shock that hits this economy. But what you see as a consequence is that when the tau shock hits, look how inflationary it is. Inflation goes up, right? That's the greenflation. That's exactly the greenflation type of idea. When you have this increase in tau, that's going to be increasing marginal cost, it's increasing mitigation spending, and thereby you're going to get that inflationary effect here. And on output, it has two different forces, right? One force is you have more mitigation expenditures, but there is, of course, a drop in consumption at the same time, right? And so the net effect on output is depending on the sum of the two. So this is having all these, effects, all these things that, we are going to discuss next. Last but not least, and I want to make sure you understand that as well, this is a one-time shock. This is a one-time shock in tau. So there is in period 1, tau goes up by 0.1 and it stays only up for one period. If you say, no, I want the tau to be for 10 periods rather than one period, well, then you're going to change just one thing. You're going to say 1:10. So this is now an increase in the carbon tax by 0.1, so a 10% carbon tax for 10 consecutive periods. Okay? So for 10 periods, you're going to impose that 10% carbon tax. And what you're going to get then, you're going to get a figure that looks like this now. So now you see, like with a 10-period carbon tax, you're going to get, of course, that carbon tax is up for 10 periods, you will get more persistent inflation increases, right? You have, for 10 periods, the greenflation effect. And then the effect on output depends again on how much abatement spending you do versus the drop in consumption. You see clearly here, the consumption effect is stronger than the abatement effect on overall GDP. You see mostly marginal costs go up. I mean, the sky is literally the limit, folks, right? In terms of what you can do with this model quantitatively, depending on configurations and so forth. What the task for today afternoon, and unfortunately tomorrow morning, is to finish the slide deck on the New Keynesian climate model to understand now what the authors do with this model quantitatively. What is the analysis they are doing? Unfortunately, for time reasons, we will not be able to go through as in detail the replication code kit, because but let me just open it for you and show you the replication code kit that we have. So the second code file on OLAT, right, or on Moodle, let me show that to you, is having their replication codes. So if you go to Moodle, if you go to our Moodle website, right, there is this file, New Keynesian climate model. Right? So this has their replication codes. With everything that we discussed here, you should be able to understand this code kit much better. So let me give you a sneak peek on this. So when you open this file, this folder, you have all these codes. So there's a lot of codes in there, but maybe the most important one is this modfile.mod. This modfile.mod on the replication code. And what you see is there, it's giving you exactly the same structure as we have in our node-trends code kit. There's variables defined. It's more involved, but it has the same type of structure. There's variables defined, there's shocks defined, then you have the parameters defined, right? I mean, it's more involved, but it's the same type of spirit. Then we have lots of parameter values here, right? So these are all the parameter values coming from the estimated model. I'm just assigning it. And then last but not least, we have the model. And the first new thing in this model is now the trends. So they're putting the trends back into the model. Right? We deleted the trends on the no trends part of the model. Now they put the trends back in. So we have more endogenous variables. So this is the inflation target trend. This is the technology trend. Literally like more equations, but no substantive difference to what we have been doing here with simple code. And then you have again our IS curve, the Phillips curve. It's a little more complicated, and that's why I decided to strip that all away to get you to the gist of the climate code, right? But literally, it's not like a thing that is impossible for you to understand with everything we did. Then we're going to have the steady state model, exactly as before, right? You're using an external function to calculate the sum of the steady states, right? So here, for instance, now you're using this function to calculate the steady state for Z and M. That's it. And at the end of the day, you're setting this up for for the solver. That's it. And then so the file is more complicated, but it's now extending this what we've learned. And then you have two key mod files. One is run simulations, where you are running simulations from this model, and one is running impulse responses. So what this running IRFs.mod does, it takes the model, takes the shocks, and computes impulse responses from the estimated model. Now let me run that on my computer, and you can run that too. So if you go to this, first of all, you have to go to this folder, please, right? It's important that you are in the right folder, right? And then you're typing in Dynair, for those who can, with the right toolbox, right? Run underscore IRFs.mod, semicolon. And then you hit enter. And now that's going to take a little bit of time now. So what's going to happen is that now you're solving for many impulse responses. You're drawing from parameters, and you're computing lots of impulse responses. See how fast that is? And it's going to, after it's been finished, it's going to give us the impulse responses from the estimated model, where you also have, some uncertainty bands, where you get the impulse responses. So That's going to take a minute or so. But it literally does take the model, impulse response, change the parameter value, impulse response, change the parameter value, impulse response. So it gives us, as we're going to see, the impulse responses with a measure of uncertainty coming from the estimation of the model. So it takes some while. I mean, it does this for a couple of hundred times, you see, but we are already halfway through now. Okay. And then it's going to pop up in impulse response. Are there any questions in the meantime for what we did so far with the New Keynesian Climate Code? Anything that you guys are wondering about? Yeah. Okay, so not all authors put replication codes on their websites. So this replication code kit comes from the website of Gauthier Fernandel. So if you go to Gauthier Fernandel, who's one of the co-authors, he put this replication code kit on the website. And I took it and took out the complicated trends part to do the no trends code we did together. But you know, all these files are on their author's replication codes. Now, many people do post the replication codes, but not all people. Like for instance, the next paper that we're going to study doesn't have replication codes yet. It has some, but not all of it. And so it depends always on the author whether it is actually replication codes or not. So here we go. This is how this now looks like. When you have now done this, you see you have like always 3 lines. The middle line is the mean response, and the thin lines are the 95% confidence intervals. So you're getting also measures of precision for when a shock happens, right, in this economy, how the model economy adjusts. And then you literally, can take it from here, folks, that, play with this computer code, examine it, and you can apply this. I think with everything that we discussed so far, you should have an understanding first. How is this solved? What's the solver? And what's the computational setup? And now it's a sandbox to play with, basically.
Sorry, in the no trend version, right? So
yeah.
The monetary policy is quite straightforward to interpret, but if you include the trend, right? So whatever
That's
target
right.
you
Yes.
have, right? So it's a moving target, right?
That's a moving target.
So how can you integrate?
Yeah. Okay. How can you integrate? That's a great question, folks, and that's why we are going to go back to the slides, because that's something that we still have to discuss. Okay? So let's go back to the slides, and also this is our New Keynesian climate model. So far, right, let me maybe go back here, we spent a lot of time in this course understanding this model setup, right? So we've done a lot of work getting these 4 equations and understanding those 4 equations. Then, we spent a lot of time on understanding what does it take to get this into the computer. Okay. Now what we need to do is we need to understand what's the economics, what's the intuition underlying this model. And there is some work that we still need to do. Okay. And so that's what I want to do next week. So the key idea is that, when you are looking at this, we have now still to cover about 20 slides that actually take us through, some of the estimation. I'll be brief on that, but then how does what are the implications for monetary policy? So the question you're asking, is exactly this: how can we think about understand what monetary policy does and its moving targets and so forth? So that's why I want to now start with the remainder of the slides of this slide deck. So first of all, what does estimation here mean? Okay, so how can we think about what the authors are doing when they say estimation? As you have seen from the computer codes, there are lots of parameters. And the results of this analysis is going to depend on the model parameter values. What model parameter values are the authors using? Well, for many parameters, not all, but many, they are actually estimating the values of the parameters. And to do so, they are taking data from 1985 to 2023. So they wrote this paper in 2023, or late 2023, that's why they used this sample. And they take data from the world economy. So they take the position that this model is a model for the world economy. So for the economy of the world as a whole. So this is not a model for Vietnam or for Germany, but a model for the entire world. That's how you do this. So they take 4 time series, the data that they say they are observing are 4 time series. So this is world real output growth. This is the growth rate of world output. This is the growth rate of a worldwide measure of inflation. It is a measure of the worldwide average short-term nominal interest rate. So think about you go to all the countries in the world, you take an average of the interest rates in this country. That's the short-term interest rate. And you take the worldwide CO2 emissions growth rate. So those are the 4 time series that the authors use to estimate the model. Okay. So they are forcing the model to explain that data quarter by quarter. So they're literally explaining that data quarter by quarter by quarter by quarter. That's the key. Alright, so then how do they do this? Well, they do what they call the solution and filtering using the Ferrand-Taylor. That's the perfect foresight solver. Now, this is what we studied in the previous hour, right? So this is what's called the perfect, right, foresight solver. And then they have, of course, augmented that to estimate the parameters of the model. So it's not trivial. That's where the research is. There's added routines to estimate the model. And the remaining slides are supposed to help you understanding what estimation means, okay, in their word, in their language. So in particular, you can write the model with these 4 equations. That's how you can write, quote unquote, the model. So you can write the model in the first block, which is the trends. So these are the trends. Okay. So all the wiggly variables are just the 5 trends. We can write, there's the vector of trends. So this is the vector of trends. So this is the inflation trend, the steady state trend, all dumped into this vector. So y is a vector of trends. Okay. So you can think about, yt tilde is a vector of pi star z and so forth. Okay. So that's a vector of variables that they have. So then the 2 is essentially the model equations. 2 is a way to write the model equations. So these are the model equations. So there, you have our 11 equations and you stack them. That's all in here. So y is a vector, that has things in like inflation, output, and so forth. Okay. So y is this vector that has all the, all the model variables in. It's a vector with all the model variables, and you can write them as functions of the trends and other stuff. Finally, there is a script or a calligraphic y, which is the measurement or the observables. Okay? So this is the model, right? This is this vector, but of course the model has things like marginal cost. Maybe I should add that. There's marginal cost there, and many more, right? All the model variables, which of course we're not going to measure. So this is the script y is this one. So let me write this. This is like 100 times script y. Okay? That's what this script y is. This is our vector of observables, and so that's what this is. This is the data, if you like. This is the data, and then this is how our vector of model variables translates to the data by multiplying it by a matrix. That's a so-called measurement matrix. Basically, it says inflation is the first object in my model, inflation is the third object in the data, and then there's the 1,3 object that in this matrix that connects the model with the data. And then finally, they assume that the shocks are all normally distributed with some variance. So where do we see the parameters here? Well, the parameters are in these theta vectors. Okay, so the parameters are in these theta vectors. That's a vector of all the variables they're estimating, the parameters they're estimating. So for instance, one parameter they're going to estimate is like they're going to estimate what model parameters do we typically have? You know, there's like the theta one, theta's bad example here. It's a bad example. So they have, for instance, let me check what variable. I'm going to come back to that in a second. Hold on. I'm just going to see what variable, what do they estimate? Oh, sigma c and omega, exactly. So we have parameters like, you know, utility parameters, sigma c, or sigma n, and omega, and a lot of other parameters. Okay? So you're stacking all the parameters that you want to estimate into this big vector, and that's what they abbreviated with this capital theta. Okay. So then they are estimating that parameter vector theta. That's what they're doing. Okay? That's all they're trying to do. And how do they do this? Well, that's a little more complicated, but essentially, you guys have heard about maximum likelihood estimation. They do maximum likelihood estimation. That's what it is. They estimate. So looks complicated, and it certainly is complicated, and it's beyond our course to understand the details of that. So that's not going to be exam relevant, right? I want to give you an idea intuitively what the estimation does, but it's beyond our scope to understand every little piece and bit in the estimation. That's too much, too complicated. But essentially what this means is they're doing maximum likelihood estimation. So this is like maximum likelihood estimation. So they're trying to maximize the likelihood conditional on the data that, you know, they find the parameters that make this model explain the data in the best way. So an analogy is you can think about an OLS regression, right? You have heard about an OLS regression, you know, as an example, okay, that you can estimate with maximum likelihood, where you're saying, like, suppose you're regressing y on a parameter beta and some data plus some shock, right? That's the typical OLS regression that you guys have been running in your life many times in your econometrics classes, right? Where you're conditional on the data, x and y, you're looking for what is the blue estimator, you know, beta, so that the model explains the data in the best way by minimizing the squared residuals. So in other words, you know, this one is the vector of parameters that is comparable to the vector of parameters that we are looking for. We're looking for what parameter values are we, you know, do we need to explain the data in the best linear unbiased way. And so this is an OLS type regression where I mean, it's more fancy, but intuitively that's what the estimation is. Any questions on this? Again, I want you to understand the intuition and don't worry about the technicalities. Slide 24 is not relevant for the exam that you need to write this down, but I want you to understand what's going on behind the scenes. So then you can visualize the estimation, right? You can visualize how the estimation works. So suppose you have data, right, from 1985 to 2023. So that's your sample. That's the sample that we have from 85 to 23. And then, you know, suppose those dots is a time series for output growth or for inflation, just as an example. That's the data that you have in your sample. And then the estimation works as such that suppose you have, you know, you have a candidate for the parameter vector, right? You have a vector with all the parameters, and then what you're going to do is you're going to compute first, given the parameters, what are the trends in this model? How does the trend look like? And here, for instance, how does the trend for the level of GDP look like? And it's going to, you know, flatten out because growth is going to come to a halt far outside the sample. Okay? That's the first thing. You're going to compute the structural path. And you're going to look for a path that the trend cuts through the data in the best way. You know, we don't want to have a trend that does this, because then the trend would be always above the actual data. The residuals would be big. We don't want to have a trend that looks like this, because the trend is very below the data, so we're always going to have big residuals. We're looking for a trend that cuts through the observations in the best possible way. So then, conditional on the trend, we then are looking for the shocks. Okay, now comes the time that we're looking for, okay, the deviations from the trend. So that's a shock. We're looking for, find that shock that the model needs to explain the data. So that is a shock. Find a shock. Remember, we have these 4 shocks, right? And we're finding what 4 shocks do we need to explain these 4 time series: output, inflation, emissions, and the interest rate. So we're trying to find a shock epsilon. That means, you know, the discount factor shock, a monetary policy shock, and emissions, and so forth. Right? And we do so that the model explains the data in the best way. Now, there's a little bit of a subtlety here. We don't want we don't want something like this, right? So this would be, you know, too short. You know, when we have this, we want this kind of smooth. We want this adjustment to be smooth. Okay, going back to the trend. But we literally find these, you know, have to find these shocks, and such that in each step, when we find these shocks, all the model equations need to hold. Okay, so the entire 11 equations by 500 periods is like, you know, they all need to hold, and they need to explain the data. And that's going to give us these shocks. So we have basically, we go through the sample step by step, and we go in and computing recursively these shocks. You see, then once you have this shock, now you say, okay, I need to explain this data point. And then you have another shock down here. And in each point, when you have a shock, you have to solve the nonlinear model and how it comes back to the trend. And then you go to the next. Here's another shock. So long story short, you're going through the sample step by step and compute the shocks you need to explain the data step by step. That's the sequence of shocks you need to explain this data. And once you have these shocks, then you can do maximum likelihood estimation, right? Once you have a sequence of shocks, you can then compute what is the likelihood. And then you can try to find, you know, change the parameters and recompute the likelihood, right? I mean, the whole idea of maximum likelihood is, this is like for a given parameter value. Like, you know, suppose as an example, like, for some, for instance, for some, sigma c, for instance. You do this. And then you say, okay, let me consider an additional or an alternative sigma c, okay? Let me say there's a sigma c that is different from sigma c prime, that's different from the original sigma c. So you say, let me start sigma c equal to 1. Go through this, find the shocks, compute the likelihood. Okay. Then you're going to say, okay, let me try sigma c equal to 2. We do this. Compute the trend, find the shocks, compute the likelihood. And then you compare the 2 likelihoods. And if sigma 1 is higher likelihood than sigma 2, then you're going to say, okay, the sigma 1 has a higher likelihood. And you're trying to find what value of sigma do you need to have so that you're maximizing the likelihood. That's the idea. That's the idea. So we're looking for what parameter values make this model fit the data best. Any questions to this? And then comes the most exciting bit. So this is first of all exciting, but then what they then do, and that's what we're going to spend a lot of time to today, right, is, and they do these so-called out-of-sample forecasts. They say, give me the last observation in the data that I have. Now I have a model that fits 50 years of the 40 years. So this is 40 years of past data. The model explains 40 years of past data. So that's good. So I have a model that can explain the data that we have observed in the past. Right? That's a credibility exercise, essentially. This model explains the 4 time series: inflation, output, emissions, and the interest rate fairly well for 40 years of the past. That's good. But then I'm going to say, okay, what do I do now with this model? Now I'm going to do experiments with the model. And one experiment is I'm going to forecast how does this economy evolve for the next 75 years. And that's what they call the out-of-sample forecasts. You can say, okay, I am in the third quarter of 2023, and now I'm projecting 70 years in the future. How does inflation evolve for the next 70 years? How does output evolve, and so forth. So that's the idea. Any questions on this? Okay. So, so one thing that they're all putting into this estimation that makes this a little more complicated is that they are also putting in a path for tau, a path for the carbon tax. So they are putting in a path for the carbon tax. Okay? In other words, they take the model literally and say, okay, there's what's called the so-called Paris Agreement. Okay? The Paris Agreement is many countries around our globe have agreed to reduce their emissions to zero by the year 2050. So what they do is they calculate a hypothetical path for pi that they call pi star, a tau. For tau that they call tau star, so that the emissions are going to zero by the year 2050. Okay. I'm going to fast forward here and don't go there. But the idea is, this is for instance emissions. This is the year 2023, and they're computing what path for tau do I need to have so that emissions are going to be at zero, in the year 2050. That's one baseline they're doing. Okay, so that's the idea behind this, like the Paris Agreement is that. Now then, they of course are careful and saying, wait a second, is it actually going to happen that all the countries on our globe are going to make this happen, that emissions are going to be zero in 25 years from now? Maybe some countries are not. Maybe some people actually don't believe in that. And that's why they are allowing in their calculations that the people actually differ in their beliefs from this path for the emissions. Okay? So, and rho is going to be a crucial parameter. So what does rho measure? Rho measures how confident are households and firms that we actually are going to go to zero in terms of this emission tax or in the new emissions. Okay? So when rho is equal to 1, right, then people believe exactly what the agreement, the Paris Agreement says. Notice that when rho is equal to 1, or when rho is equal to 1, the emissions tax, tau tilde, is exactly equal to tau tilde star. So everywhere in the model where you see a tau tilde, it's going to be equal to tau tilde star when rho is equal to 1. So this means everybody believes that emission tax. The counter is that when rho is equal to 0, notice that people are believing there's never going to be any tax. So tau 0 means whatever that Paris Agreement is, people make their decisions of how much to consume, how much to produce, under the expectation there will be never an emissions tax when tau is equal to 0. So that way they parameterize how much does this economy actually believe that we're going to be into the Paris Agreement. And the beauty is now, of course, everything is going to depend on this rho parameter, and that's among the estimated parameters. So that's one parameter they actually estimated. That's going to be estimated. So we can think of estimating this parameter in terms of the past data to extrapolate going forward. All right. So how does this tau star look like? And apparently the tau star looks like this. Okay. So if you go into the paper and you read what is this tau star parameter or tax going to look like, it is 0 until approximately 0 until not so long ago, and it's predicted out of sample to go up like this very steeply. So in other words, what is on the y-axis? This is the amount of US dollars per ton of CO2 emissions. And in other words, to actually get to zero emissions, the required carbon tax is going to be very steep, and within the period of, let's see, by 2050, so over 20 years in time, we're going to see carbon, according to the model analysis, we're going to see carbon taxes going up from about 0, or it's already there, it's like 20 bucks to about 150 bucks. And then when emissions are actually 0, interestingly enough, the carbon tax can go back a little bit, and that has to do with, of course, that abatement, mitigation, improves. The technology to mitigate becomes cheaper over time, right? So when we discuss these abatement technology, let's go back there. Discuss the details on the abatement technology, right? There was this parameter, theta 1t, that is the cost of abatement, and that becomes cheaper over time. So this theta 1t, right, declines, so every unit of mitigation becomes cheaper, like filters and more energy, more emission-friendly cars, they become cheaper to do over time. And that's why this optimal abatement trajectory, and once emissions are 0, it allows actually to backtrace, to back up a little bit on the tax because of the technology improvements to mitigate and abate. So that's the path that you will need to get emissions to 0 by 2050. And then you can think about in your mind, you can say, okay, so this is the, when rho is equal to 1, then what people actually plan with is going to be exactly this path. When this var rho is equal to 0, people are going to think, it's going to be 0 forever. That's the key. All right. So then, the model, they cannot estimate all parameters, so that's why they're still calibrating several parameters. Okay. So why is that? Well, these parameters typically are not identified by the model. If you think about this from an OLS regression perspective, so back here, when you think about this as an OLS, right, you can suppose you're writing an OLS like this, yt is equal to beta 1 plus beta 2 times xt plus epsilon t. So suppose you have two parameters you want to estimate, beta 1 and beta 2, but you only have data on x and y, you can only identify the sum of the two parameters. You cannot identify this or that separately. So that's why you can only estimate one parameter, like you can only estimate the sum of the two. So that is, you have to calibrate at least one to then estimate the other. That's the basic idea. So that's why, in general, in many macroeconomic models, you will never be able to estimate all the parameters, and these are the parameters they are fixing a priori. But more importantly, here are now the estimated parameters. So those are the parameters that the authors estimate. And this is the holy grail column. What is this? These is the values of the estimated parameters. These are the values of the estimated parameters. So, so that means the posterior mode, that's the most likely values of the model parameters. And then you also have a confidence interval and so forth. But if you look at it, so what are these parameters, right? So first of all, these are the exogenous processes, right? So these are, it's the demand shock, the standard deviation, the price, and the emissions shock. So those are the standard deviations of the shocks. And here are the rho, the AR1 coefficients. So that's what the estimation is going to give you. And you see some of them are highly autocorrelated, and others are less so less autocorrelated. Okay? So some have AR coefficients of 0.5, others have 0.95. And then they have a lot of structural parameters that they're estimating as well, right? Where you see the estimated variables there. Like for instance, the risk aversion parameter is 1.13. Sigma C in the utility function. You have also a parameter like for the Rothenberg adjustment costs. Something like that, right? So you have a Rothenberg adjustment cost parameter where the data pins that down to be 118, so as to match the inflation dynamics. So there's a lot of parameters that they are estimating, and these parameters are typically pretty well identified. So you're going to see a lot of, for instance, the monetary policy, GDP response, or the inflation stance is the response by the central bank to inflation. And so that's a very interesting set of parameters. And how would you come up with these parameters yourself without estimating, right? I mean, it's very unlikely that you will hit exactly that combination of parameters. Like here's the initial inflation trend. So initially inflation was at 13% on average in the world in 1985. So this is the 1985 trend inflation rate, 12%. Much higher than where we are right now. Here, that's the initial interest rate, that is 0.8, it's 8%. Omega is the share of the low productivity guys, right? It's very low. It's only 5% of the classroom are unemployed on average. 95% are full productivity employed workers. So that's so much for the discounting in terms of this model, right? The discounting isn't super strong, but it's enough to get by the problems of that we have. So with those parameters, okay, with those parameters, you can now display the data versus the trends. Now, importantly, the model explains every little detail in these blue lines. So every bullet, the model explains exactly up to the 7th decimal. Okay? So if you ask the model, what is the data looking like, at each point in time, by the way that this estimation works, you explain the data at every point in time here. That's great. What this slide does, it shows you the implied deterministic paths. It shows you how the path for the interest rate looks like, how the path for inflation, how the path for output growth in terms of the trend looks like. Right? So how much the GDP growth declined in sample, how much inflation target declined in sample. That's how you have to read these lines. But there's been a decline in inflation, interest rates, and the growth trend in the world economy in the last 40 years. And that's how the model interprets that. So in other words, when we introduce these trends, right, I think sometime last week, when we introduced these trends, just go to the introduction of the trends there, right? When we introduce all these trends, right, there, and there, and then there, and one of the things, of course, is that we didn't know at the time what are the parameter values underlying these equations. Like, what is this curly L? What is this delta Z? What is this rho pi? We didn't know that. They have estimated those parameter values. And once you have those parameter values and an initial condition, you can then just draw these trends. And that's what they do on these graphs that we just examined. Okay? It allows us to access the trend behavior of this economy. All right. Any questions on this one, guys? Go ahead, Lee. Great point. How well is this identified? So Lynn asked a great question. So let's go back here, right? So one thing I said is that they are doing these out-of-sample forecasts, and this parameter here is kind of important. So first of all, what is the value of this parameter? And then you ask implicitly that, okay, how can we pin down this parameter if we have so little data in the past, right? That's the question that you have. So let me try to answer that. First of all, what is the estimated var phi parameter? Okay. So let's go to this table. Let's try to find it. What is this parameter value? Can we sort of say identify it? Exactly, right? There we go. This is where it is, right? So this is the parameter. So importantly, right? So this comes out at about 0.5. So Asians believe about 50% of their tax increase is going to happen. So we're not going to go to zero in emissions, but we go to relatively small amounts. Okay. That's the first thing. So the parameter is 1. It's not 1, it's 0.5. And then Lynn asked a very good question in the sense of, so what identifies now this? Where does the identification come from, right? And there, my interpretation is that it's only in the very last couple of years in the data where this is going to come. So the carbon tax is already up a little bit, but not much in the last 2 to 3 years. Many countries have started to introduce these carbon taxes, like in 2019, 2020, 21, 20, but only for a few years in the past. Okay? And that's where most of the identification must come from. And what do you need is, you need how do these carbon taxes affect emissions, right? That's the idea, right? There must be, when carbon taxes go up, emissions must go down, okay? And given that emissions are a time series, like here, right? And emissions are a measured time series. Emissions are a time series that are measured, that will allow you to identify the relationship between actual carbon tax increases and the emissions that we observe. But only for the last couple of years in the data. So my hunch is that had they stopped the measurement like in 2015 or so, there would be no possible to identify Bordeaux. Okay. So the identification comes from, if you maybe look at that from that perspective of the graphs, the identification of tau must come from the last couple of observations in the sample. That's the idea. Because this tau, is of course going to affect the shocks that you will need to explain the data. And then in the estimation you're trying, shall I have a high tau, a low tau, okay? And then how is that going to affect? And then the bar phi is going to kind of give us the idea of what people effectively are calculating. So it's an important dimension to really understand that, yeah, it's
So if after they introduce the Paris Agreement,
yeah.
we see is any relevant, to the variation of the shot between shot among the
Can you explain again? Sorry. So
turn right to the graph. So, is it any relevant or connection after they introduce the Paris Agreement that affect the correlation of the shot?
I mean, anything after 23 is not part of the estimation. So here you have to say everything here is not part of the estimation. That's so. In the estimation, you stop here, and that's all you see. This is something we're going to do now. We're going to do experiment with the estimated models. We're going to do experiment next. But so is your question about this part? No. What's the question?
So this time is the time that they introduced Paris.
Yeah.
So for this time to this time, is then relevant that after they introduced the Paris Agreement affect the evaluation
Yeah, it does. Oh, yeah, exactly. So that's the idea. I mean, so it will affect it. So the Paris Agreement affects this in the sense that, okay, I think I understood this. So the Paris Agreement, if you look at these emissions, right? So the Paris, I mean, we have emissions growth in our data. And once Paris was, was decided upon, for a couple of years, we have that emissions behave differently than in the past. That's basically the idea, right? So we have emissions do whatever they do, but after Paris, they have changed a little bit their behavior. And how do we explain that change in the behavior? It's with the emissions tax. So the emissions tax will come alive, and but the emissions tax that we need is going to look different than what Paris has actually imposed us to do. Paris has already implicitly a higher emissions tax that we should see, but in practice we have a lower emissions tax that's effectively implemented, and that's the belief, that's the bar 5 here. So long story short, it's the difference in the emissions growth rate in the last couple of years that allows us to identify this parameter. I mean, that's how I would put it basically. So, we require to explain the data. The authors now require this change in emissions. Okay, I hope that's helping, folks. So, what's the big idea? I'm going through these slides on the estimation and the estimation results, so you have an idea of what the authors do to pin down the parameters. Okay? I do understand that there's limitations of how detailed we can go here. Okay? This is really advanced material. You can do an entire course on just the estimation. Don't get me wrong, it's complicated and it's very advanced. It's really research frontier material, and it's beyond the scope of our course to understand every little bit and piece of the estimation. If you understand the big picture, that's enough. Okay. They estimate these parameters to hit some time series, and then they do out-of-sample forecasts. That's the idea. So what I want to do next with you is, I want to then go through for the remainder of today, and we're going to go 5 minutes later because we started 5 minutes late today. We're going to finish at in 15 minutes. I want to start at least making a run at what did we learn from this paper? What are the key takeaways? I mean, we've been investing a lot in the model, in the codes, in the estimation, but we should take time to understand now what does this paper teaches us as readers or as customers, okay? And that's what I want to do next. All right. So, and they call that the so-called anatomy of the green and climate inflation. So and now what we're going to learn is through the lens of this model, what do the authors assess climate inflation and greenflation to be quantitatively. And they are always in this paper comparing 3 scenarios. They are comparing what they call the laissez-faire. So laissez-faire basically means no change, 0 carbon taxes. We're just going to let the economy evolve without any carbon taxes. And we're going to be able then to study how does the economy look in that scenario. So going back to these forecasts, one is here we're saying, okay, let's have the carbon tax equal to 0 for all periods in time. And how does the world economy evolve going forward without carbon taxes? So that is, by the mechanics of the model, the same as setting the var phi equal to 0. That's a var phi, that's not a var rho, it's a var phi, no? Anyway, you know the symbol. Okay. So then they go in the opposite direction and say, okay, let's suppose, going forward, the world pulls its act together, and we're going to land up with 0 emissions in 2050. Okay. So let's have the full Paris Agreement, simulation, saying, we're putting in that pi star trajectory, everybody believes it, and it's actually going to be implemented. How does the world look like that? And then they are comparing the intermediate case and saying, okay, let me go with the estimated model and take a look at, with that estimated value, that's somewhere in between those 2 maybe extremes, if you like. So that's the third path they're looking at. Go ahead.
So I just want a quick
Yeah.
clarification. 0 emission, you mean like the stock value at that time is 0, not the damage is 0.
Careful. We don't say 0 emissions. It's a 0 tax. It's different. It's a carbon tax.
Oh, okay.
So this is the scenarios based on the carbon tax. That's the idea. Okay. So we have with phi 1, right? And this is the path for the emissions tax. And so with this one, with the emission tax going like this, the emission level is going to come down to 0 by 2050. Conversely, when we have a 0 emissions tax, emissions are going to keep high. That's the okay. So good clarification question. Need to be alert on this one. Lee? Yes, that's right. When you have a zero carbon tax, you're making no abatement spending. Absolutely. Right? Zero carbon taxes, there's no incentives for anybody to mitigate. All right. So how does this now look like? You know, what are the key results? Okay, and so here are these 3 transitions, and these are model implied projections, aka forecasts. In particular, it's out of sample forecasts. Okay? So this is now the forecast going forward. You know, this is the year 2023, and they are projecting 70 years forward. Okay? That's how you have to read these graphs, basically. So they're taking the model to the last observation, okay? Taking the model to the very last observation, and then what we see now is we see these graphs, we see these paths. That's what we see now in the figure that we started to discuss. Okay. All right. So what do we see first? We see the carbon tax. We see the emissions. We see output. We see inflation, and we see the normal interest rate. Okay. That's what they give us. And then they give us 3 lines in each graph. Okay. So let's start maybe with, and then in terms of the units, it's all defined, but this one's important. This is quarter-on-quarter inflation. Okay. So this is Q on Q. So this is Q quarterly inflation. So in other words, if you want to interpret this with the numbers that you read in the newspapers or in the Wall Street Journal, you need to multiply these numbers by 4 to annualize them. Okay. So you need to multiply by 4 to annualize. Okay. So long story short, you multiply this by 4, then this is 8%. Okay. Or you multiply this 0.5 by 4, then this is 2%. So these numbers are sizable. 2% inflation, that's kind of sizable. All right, but let's go slowly here, and let's go through this step by step. And let's maybe start with the laissez-faire. Okay. So let's start with the laissez-faire. So that is, you know, the tax is equal to 0 all the time. Okay. And that's what you see here. Now, this is when you have no taxes implemented at all in this economy. What do we see as a result? Well, this is the level of carbon, you know, emissions that we are estimating right now. And you see, without any carbon taxes, there's no abatement, right? There's going to be a little bit of a blip, but long story short, emissions are going to stay up for quite some time. Okay? So emissions are going to be up for, you know, because there's no abatement, emissions are going to keep rising. Now there's this little blip here that comes from that the economy went through a recession. This is the inflation surge, you know, post-COVID recession, and that's why there's a little bit of a, you know, a blip in emissions there. But you know, as the economies are recovering from the latest recession in the data, we see emissions are going up. What's the implied path for output? You're going to see here output falls, but then it keeps on falling and falling, and actually it's going to keep falling forever. So output will keep on falling with the laissez-faire forever. You know, so that's an important, so to say, relative to the level of 2023. So what's the intuition for that, folks? Somebody think about why is output keeps on falling and falling and falling?
Because it's keep eating up to the productivity.
Exactly, right? So if we write down the production function, right, let's write down the production function. So we have yt is equal to, we have this phi of mt times nt to the alpha or something, right? When the emissions are high, that thing is going to be negative, right? Or not negative, it's a down force on output. And as Min, you know, emphasized, right, when emissions keep being high, it's going to add to the stock of carbon, and the higher the stock of carbon, you know, the more detrimental is the effect on output. Very important. We understand that the economy is going to go down the drain, basically. Not go down the drain, but it's going to be it's going to be below its 2023 level. That's how it's thinking about it. So what does this do to inflation? Well, in terms of inflation, you're going to see that because of that effect, you're going to see inflation goes up, but then inflation is going to come down. But look at the numbers here. This is in the 2020s. This is in the 2040s. Over a period of 20 years, inflation is going to be elevated relative to here, right? So this is like our current level of inflation, like about here, and then for 20 or so years, we're going to have elevated inflation. The red line. Can somebody help me with a buzzword? What buzzword would we give to this in terms of the two buzzwords that we had on the first slide that central bankers are worried about? Climate inflation. The red line is climate inflation. This is climate inflation. This is solely the effect, right? So this is solely, here, this is when the last observation is, when the last couple of shocks, they faded away at some point. So starting like in the mid-2020s, all the way to this, right, all this trajectory is the climate inflation that will take place. There are no discount factor shocks, there are no technology shocks, there are no monetary policy shocks. All these shocks are zero. So this red line is entirely driven by, the climate change. How did climate inflation operate in this economy? What produces this climate inflation? Climate damage. Marginal cost, right? We know that marginal costs are a function of the climate damage, right? It's exactly it. So marginal costs are a function of climate damage. And if climate damage hits, that's going to increase marginal cost. So when this is affecting marginal costs in a positive way, this thing is going to push up marginal cost, and thereby it's going to push up inflation. Very important. So in other words, we see that in this economy, because of climate change, we see reductions in output as well as increases in inflation because of climate damage. Now, is this large or is this small? Is this quantitatively negligible or not? My way of reading it is, if you look at this, maybe starting here, for a period of 20, 30 years, if you take the average of this red line, it's about maybe 0.5% or so, 0.5. So the quarterly rate of inflation is 0.5% elevated. The annualized is 2%. So because of climate inflation, right? So let's write this out, right? So this is about 1/2 or per quarter, or 2% per annum. So quantitatively, climate inflation says, climate inflation gives you 2 extra percent on inflation over a period of 30, 40 years. That's the worst case scenario for central banker. So suppose you're having an inflation target of 2% in your economy, and climate inflation produces, instead of 2%, 4%. That's the end of the world for central bankers. It's like the hair will be on fire. It's not like for 2 to 3 years we have like a little elevated inflation. No, look at this. For decades, inflation will come in higher than what central bankers have anticipated. That's undermining central bank credibility. That's undermining, a lot of the things that central bankers actually need. So that's where the problem comes in. That's a big problem. Now the central bank tries to fight this. That's what this red line is, right? Tries to fight it. But it's not fighting it in a way that's going to pull it down to zero. So we're going to live with, according to this paper, with a period when interest rates are going to be elevated for long periods of time. So through this lens, like things like the zero law bound are going to be less likely to happen. All right. Now I want to use a few more minutes to think about the Paris Agreement part. Right. So this is the tau tilde equal to tau star. So this is now the case when this is the tax to put in to drive emissions to zero. So we're driving emissions to zero, and everybody believes that, right? That's the other extreme, if you like. And then thereafter, emissions stay at zero. So what do we see here? Well, we see what we call in macro short-term pain and long-term gain. We see that GDP goes down by more than under laissez-faire. And tomorrow we're going to learn why that is the case. Tomorrow we're going to decompose why that is the case, but we're going to see what we see is that output goes down by more than under laissez-faire. So that is, nobody would vote for that, right? You know, if you see this green, if I only give you this, and I'm going to say, look, you know, which proposal will you vote for? The red or the green? You would all vote for the red. Right? Nobody would vote for the green. I mean, this is like, my income goes down by 3% here, there it only goes down by 1.5%. I would certainly vote for this and that. But if you see the full picture, then you see that with the tax, you're going to see that output actually recovers more than here. So there, you know, we're going to be permanently richer compared to this. So there's short-term pain and there's long-term gain. And the reason here is abatement spending. When you put in that tax, what it's going to do is there's going to be more investment in mitigation, but there's also going to be a reduction in consumption possibilities for households. There's a crowding out effect, and we will be discussing that tomorrow on these types of slides. Right? We will decompose the term, you know, the output effect into a consumption effect, into an investment effect, into a wage effect. We're going to do all that tomorrow. Right? But I want to kind of drive this home that, you know, the output, you know, is not trivial. It's a difference, so to say, there. But now I want to come back to this. Now, with this added investment spending on mitigation, look at the inflation trajectory. And let's zoom in here. Look at this inflation trajectory now. So now we're going to get the green line, which is above the red line. So it makes it even worse. That, you know, inflation now, if you take the same time window, you know, for maybe the next decade, so this is like in the order of 0.75. You annualize it, you know, that's like 6% per annum. It's 0.75 on average per quarter. You multiply that by 4, it's about 6%. Okay? So that is, you know, it's about 6% per annum, you know, approximately over, you know, the average of 30 years. Now, can we give a name? What's that? Oh, of course. Sorry. What am I doing? You're absolutely right. I was just checking with you the weight. Fantastic job. Okay. So this is about 3%. Okay. So it's 0.75 times 4, of course, is 3. Okay. So this is 3% per annum. What name can we give to this now?
Inflation.
What's that? Greenflation? Both. Exactly, right? It's the sum, right? So this is now climateflation plus greenflation. Okay, so this is climateflation plus greenflation. So the difference is greenflation. So you can think about climateflation produces 2% extra inflation. And the difference is 1%. 1% goes on greenflation. So we have climate producing 1 additional percent on inflation, and greenflation is another 1%. So the total is 3%. Over approximately, like it's a sample, you know, from the 2030s to the 2060s or so. That's the key idea. And this is sizable. I mean, that's exactly what Isabel Schnabel, what people at the Fed at the time, you know, have in mind, that this is going to make the life of a central banker more complicated. It's not because of our business cycle. We may go in recessions or in booms. We may have, you know, shocks on top of it. But this is completely driven only by the climate change. So you're looking at now, there's now, for a central banker, it's the biggest dilemma that exists there. Because this is now elevated inflation. And in the short term, less output, but in the long term, more output. So now, the central banker, as we will see tomorrow, you know, it's like, it's a trade-off. I can push this down, you know, I can try to be more aggressive as a central banker, push this down, but it's going to bring the economy into a recession, and vice versa. By raising interest rates, I can try to bring that green line or the red line down, but it's going to deliver, if you raise interest rates, a bigger recession. And so that makes it super hard. Okay? That's the dilemma that central bankers have. That's why they are worrying about that. It's not a situation that, oh, I raised interest rate and then everything goes away. No. If you raise interest rate, you're going to make the recession deeper. So in that sense, folks, this is more like a cost push type effect that pushes output and inflation in opposite directions. Go back to last week when we discussed the cost push topic, right? This is like cost push type effects. So these are cost push type effects. It's not a cost push shock, be careful, right? This is not a cost push shock, but it's a cost push type effects. In the sense that inflation is up and output is down. Okay, that's the idea. Okay. So they all go against each other basically, and that makes it for the central bank very complicated to deal with. That's what we're going to discuss then tomorrow. Okay. Now, the estimated path, right, is where tau is equal to 0.59 times tau star. And that's somewhere in between. And now you get the point, right? You know, if your tax is somewhere in between, emissions are going to be somewhere in between. You're not going to go to zero, you're going to keep it up. So then the output path is somewhere in between. And then, of course, the inflation path is also somewhere in between. So you get the point, okay? So we actually went to the two polar cases, and then the estimated model gives you something in between there. Very, very good. So that's a first run at this problem. What we're going to do tomorrow in the first lecture, we're going to finish this slide deck. So that is, we are going to go through various decompositions and analyzing monetary policy and so forth. So the first lecture tomorrow, we're working on finalizing this slide deck. And in the second, we're going to go to the monetary fiscal interactions part. But we will take enough time to make sure everybody understands the content of these slides. Are there any questions? Okay, great. Try to be here tomorrow at 9:15 sharp, so we can go right away and we don't lose much time. We're trying to set off at 9:15 tomorrow. And it's been great to see you today, and I'm looking forward to tomorrow then. Thank you. Have a great afternoon, and see you tomorrow.